So, how in the world do you fact check the Big Bang? It sounds impossible, right? We've got these incredible, mind bending ideas about how our universe got started, but an idea is just that, an idea, until you can actually test it against reality. Today, we're going to walk through exactly how scientists take a theory about the very first moments of creation and, well, put it through the ringer.
And this is the ultimate cosmic mystery. We are talking about a moment so early, it makes the birth of the first star look like it happened yesterday. I mean, think about it. Before atoms, before light could even travel freely, what was going on in that first impossibly tiny fraction of a second? The answer to that is literally the blueprint for everything that came after. Now, the leading idea, the heavyweight champion of theories for this, is something called cosmic inflation. The concept is that for just a brief, unbelievable moment, the universe expanded faster than the speed of light. It blew up from something smaller than an atom to something astronomically huge, and in the process, it ironed out all the wrinkles in the fabric of space-time. Okay, so how do we test an idea this big? Well, we're going to treat it like a suspect in a cosmic detective story. We'll start with the initial puzzle, look at a really promising new clue from string theory, and then we're going to put it through 3 intense interrogations. We'll check its alibi against the Big Bang's afterglow, we'll see if its story holds up under some fiery conditions, and finally, we'll make sure it doesn't break the most fundamental laws of physics. It's a cosmic process of elimination. All right, let's kick things off with the initial puzzle. It turns out the simplest, most elegant versions of inflation theory, the ones everyone loved at first, had a huge problem. They made a really bold prediction that just didn't match what our best telescopes were seeing. And here's exactly where theory hit a brick wall. So think of it like this. The simplest inflation theories predicted that the Big Bang should have been incredibly loud. It should have created this powerful rumble of gravitational waves rippling through space-time. They predicted a volume level, a number they call R, of at least 0.14. But when the Planck satellite listened really, really carefully to the echo of the Big Bang, it heard, well, mostly silence. The actual volume was less than 0.07. The prediction and reality were completely out of tune. So, what do you do when your favorite theory doesn't match the data? You don't just throw it out, you look for a missing ingredient. And in this case, physicists turn to one of the most mind-bending toolkits they have, string theory. Now, this new ingredient is basically a fancy bit of mathematical code called the Gauss-Bonnet term. The easiest way to think about it is like a special rule for gravity that only kicks in under the insane energy of the Big Bang. The hope was that this new rule could act like a cosmic volume knob, turning down that predicted rumble of gravitational waves to match the quiet that our satellites actually detected. Okay, so adding this new term gives us a model with 2 tuning knobs we can play with. The first is m, which is the mass of the hypothetical particle that's driving inflation. They call it the inflaton. The second knob is beta. That's just a number that tells us how strongly our new Gauss-Bonnet term is connected to inflation. By turning these 2 knobs, you can basically create a whole landscape of possible universes. The real challenge is finding the one combination that matches ours. So, we have a new and improved theory with this huge landscape of possibilities. It's time for our first filter. We're going to take every single combination of our tuning knobs and check its predictions against the most precise baby picture of the universe we have, the cosmic microwave background, as measured by the amazing Planck satellite. These right here are the 2 incredibly specific goalposts our theory has to hit. We already know it needs to predict a quiet universe. That's a low value for R. But it also has to match another number, ns, which is kind of like a measure of the clumpiness of the early universe. You know, were the first seeds of galaxies spread out perfectly evenly, or were some areas just a little bit denser? Planck measured this clumpiness with astonishing precision. So any theory that's going to survive has to get both of these numbers exactly right. And here is the result of that very first test. For one popular model, one based on the famous Higgs boson, this new ingredient just didn't work. It couldn't hit both targets at once. Game over. But for another model, called chaotic inflation, it was a perfect match. Adding this Gauss-Bonnet term allowed it to nail both the quiet R value and the precise clumpiness value. It's still in the game. So our first filter was a huge success. It ruled out a whole class of models. But for the one that survived, a pretty big range of possibilities for our tuning knobs, m and beta, are still allowed. The key finding was that as long as the product of beta times m squared was a very specific, small number, the theory worked. We've definitely narrowed the search, but there's still a lot of ground to cover. Okay, so getting the beginning right is one thing, but a successful theory also has to get the end of inflation right. That transition from this hyperexpansion back to a hot, dense state is called reheating, and it is our second and very powerful filter. Just think of reheating as the universe's cool-down phase after its massive growth spurt. All that energy that was driving the expansion had to go somewhere, right? Well, it decays, kind of like a radioactive particle, and dumps all its energy back into the cosmos, filling it with that hot soup of particles and radiation that would eventually become, well, us. And this cooldown has a really critical role. In order to create the basic elements we see around us today, like hydrogen and helium, the universe had to be incredibly hot right after inflation. You can think of it like a cosmic oven that needs to reach a minimum temperature to bake everything correctly. That minimum temperature is about 100 giga-electron volts. Any theory that ends up with a cooler universe simply can't create the cosmos we live in, period. Applying this temperature check has a dramatic effect. It acts as an incredibly powerful filter, just wiping out huge swaths of the remaining possibilities for our tuning knobs. In particular, it really doesn't like models with very high values of beta, our Gauss-Bonnet coupling strength. All of a sudden, our map of viable universes just got a whole lot smaller. We're now down to a much, much smaller set of possibilities. So for our final test, we're going to push this theory to its absolute breaking point. We need to check for internal consistency against one of the most sacred rules in all of physics. Does the math actually hold up, or does the theory end up contradicting itself? This rule is called unitarity. Now, at its core, it's a really simple idea. The sum of probabilities for all the possible outcomes of any event has to equal 100%. No more, no less. If your theory predicts a probability of 150% for something, it's not describing reality, it's just producing nonsense. It is a non-negotiable rule of the game. So to test this, physicists model a hypothetical collision at unbelievably high energies, the kind you'd find during inflation. In this case, they calculate what happens when two gravitons, the particles of gravity, smash into each other. Then they calculate the probability of them just scattering and coming out as two gravitons again. If that probability ever exceeds 100%, the theory has failed the test. It breaks down. So what was the result? The theory passes. It maintains unitarity, but there's a condition. It only works as long as that coupling constant beta stays below an astronomically high, but still finite, limit of 10 to the power of 10. This gives us a hard ceiling, an absolute upper bound on how strong this new interaction can be, and that ensures the theory remains mathematically consistent. Okay, so we started with this huge, wide-open landscape of possibilities. We've filtered it through the cosmic echo, we've filtered it through the fiery end of inflation, and we've checked it against the fundamental rules of physics. So what's left on the other side? Here's the journey we just took. We started with a vast landscape of possibilities. The data from the Planck satellite came in and carved out the first big piece. But the real game changer was reheating. That temperature check acted like a razor, eliminating almost everything else and leaving us with this really narrow range of options. After all of that, only a tiny specific window of possibility remains. And this, right here, is the scientific method in action. It's beautiful. We started with a purely theoretical idea, this little tweak to gravity inspired by string theory. But by relentlessly, ruthlessly testing it against real-world observations, we've basically cornered it. A huge, open question has been narrowed down to a focused, well-defined problem for scientists to tackle next. So is this the final theory of the universe's first second? Probably not. But you know what? That's not a failure. It's a huge success. By going through this rigorous process of elimination, scientists have basically created a treasure map. They've pinpointed the exact tiny region of parameters where a theory like this could actually work, telling the next generation of experiments and telescopes precisely where to aim their sights.